Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. In continuation with our discussion on transition metal complexes of various ligands, starting from propenyl to butadiene to cyclobutadiene, then moving on to cyclopentadienyl, as well as then we spoke about hexane, benzene complexes or arene complexes to C7H7 or 7 membered ligands, ring ligand systems that we are talking about in the last few lectures. So, in these connections not only we have looked into the homo bis aryl kind of complexes, but also the various heterolytic combinations in which there is a two different arene rings, which can be a 5 membered, 7 membered, 6 membered, 5 membered, 7 membered, 6 membered, and we have looked at all these combinations of various transition metal arene kind of complexes. So, in continuation with our previous discussion on C7H7 ligands, what we had seen is that these transition metals forms a wide variety of complexes with C7H7 ligands, not only with C7H7 ligands, but also with C7H8 ligands, and we have looked into some of the complexes, their classifications with respect to being the sandwich or half sandwich types, and then in the last lecture we have also discussed about the preparations of these transition metal C7H7 complexes. Now, proceeding further along the line, in this lecture 2 we are going to be taking up this topic on various other preparative methods that are available for this synthesis of the transition metal C7H7 complexes, and then we are going to be talking about reactivity and structure related studies of these transition metal C7H7 complexes. So, coming back to synthesis, we are going to be talking about another interesting method which involves the substitution of C7H7 benzene ring by a C7H7 ring. So, this is a substitution reaction. And this is beautifully illustrated in these particular examples, in which there is a chromium C7H8 LCl3 minus C6H6. So, this arene ring gets substituted or replaced by the C7H8 ring to give this cationic chromium complex that with Na2S2O4 and OH minus gives the corresponding neutral complex So, actually what is happening over here is the reduction of chromium over here 2 chromium 2 over here is observed. So, this is the reaction happening at the metal. The next reaction for this involves again another kind of substitution reactions in which a carbonyl of a iron carbonyl compound gets substituted with a C7H8 ligand. So, the reaction is given over here, FeCO5 plus C7H8 upon heating 110 degree centigrade eliminates a CO to give this C7H8 complex and which is bound in a eta 4 fashion to FeCO3 that when treated with N-butyl lithium gives butane, and this deprotonation happens in one of the hydrogens of this ring. Deprotonation to give this eta 3 FeCO complex. So, and this overall after deprotonation becomes an anionic complex. So, there is a lot of scope or varied reactivity of substitution reactions, where we had seen that C7H7 or C7H8 can successfully replace carbonyls of metal carbonyls. Particularly we have seen that happening in case of vanadium as well as iron carbonyl, and we had also seen that C7H8 can replace the arenes in mixed Cp chromium benzene kind of complex, as well as in benzene vanadium CO4 or Cp vanadium CO4 kind of complexes. So, the substitution reaction is suitable not only for metal having carbonyls, but also the metal bound to arene moieties. So, we are going to be looking at another new type of reactions. These are called reductive complexation, which are also used for making the C7H7 type complexes. So, complexation. And the reaction is shown over here. Zinc tetrachloride plus 4 Na sodium amalgam plus C7H8 yields this cycloheptatetraene bis complex of zirconium, as is shown over here. As is shown over here. Now, this is produced in 45 percentile. What is interesting about here is the name which suggests that there is a reduction which is happening, and indeed the reduction is happening in the metal center zirconium, which goes on from zirconium 4 to zirconium 0 in this eta 6 bound 6 C7H8 bis zirconium type complex, as is shown over here. So, there is a reducing agent which is in form of sodium amalgam in presence of this C7H8 ligands, and the metal halide produces this bis C7H8 zirconium complex, in which the metal has undergone reduction from +4 oxidation state to its 0 oxidation state. Another example which is slightly more interesting than the one that we had just spoken about, in which we will see that not only by the first step, the previous method, we will produce eta 6 cycloheptatriene complex of vanadium, but then with suitable proton abstraction using trityl cation, one can generate C7H7 bis vanadium complex and regain its aromaticity. So, we are going to be seeing this nice example as a part of our discussion on reductive complexation and the various methods that are involved in preparing in these C7H7 transition metal complexes. So, in this method what we see that vanadium Cl4 upon treatment with 2 C7H8 in presence of a Grignard isopropyl magnesium bromide, ether and light produces this eta 6 C7H8 bis complex, so which with trityl cation abstracts two hydrides, one from the top, each of the rings, so one from the top ring and the other from the bottom ring, producing 2 triphenyl methane, and as a result of this hydride abstraction, this process is called hydride abstraction. A dicationic C7H7 bis tropylium vanadium compound is formed, as is shown over here. Two plus and 2 BF4 minus. So, here we see that this is an interesting example where first the bis C7H8 complexes containing eta 6 bound. So, this is eta 6 bound heptane cyclohexatriene is formed, which upon abstraction of the hydride, there are 2 hydride abstractions which occur to give this dicationic eta 7 bound C7H8 bis complexes of vanadium. So, this reductive coupling method is successfully used in synthesizing this complex, and over here what we see the vanadium undergoing reduction from vanadium plus 4 to vanadium 0 state as is shown over here. Another interesting example of reductive complexation involves the reaction of C5H5 MCl4 C5H5 MCl4 plus C7H8 with magnesium and THF, giving magnesium CpM C7H7, where M equals vanadium, niobium and tantalum. So, here in this reductive coupling we see that this MCl4 which is M is in plus 5 state getting reduced to plus 0 state as is shown over here. So, in each of these reductive complexation examples that we have taken, what we saw that the presence of a metal halide, presence of a reducing agent and this presence of this C7H8 ligand is there, which gives rise to this C7H7 complexes of transition metal by using this method. The next method is photochemically or chemically induced sigma pi rearrangement. This is a interest sequence of reaction which uses chemical induction or light based induction of sigma pi rearrangement. Photochemically or chemically induced sigma pi rearrangement. So, in this reaction acyl substituted cyclohexatetraene with a metallate ReCO5 minus reacts with this acyl cation with a loss of chloride anion to give this cycloheptatriene containing ReCO5, which in presence of light loses a CO to give HReCO5, which in presence of Me3NO, which is a decarbonating agent, that sort of favors a loss of carbon monoxide by converting it to carbon dioxide, producing this eta 3 bound. So, in this case it is eta 1 bound. Now, when a carbon monoxide is lost, then it becomes a eta 3 bound. ReCO4, and which in presence of another molecule of Me3NO gives eta 5. Now, another loss of CO happens, giving eta 5 bound this ligand, Re CO3. So, what we see is a nice demonstration of change of this hapticity, which is sigma pi rearrangement. So, this is eta 1 bound becoming eta 3 bound and finally becoming eta 5 bound system, and this is promoted by chemical initiation by providing Me3NO, which sort of decarbonylates CO, making it carbon dioxide CO2, as well as partly by light, the first migratory insertion or loss of CO happens in presence of the light. So, this is photochemically as well as chemically induced sigma pi rearrangement, where the sigma bonded eta 1 binding gets converted to pi type eta 5 bound C7H7 ligand to the rhenium. So, this is a very nice example whereby this C7H7 complex was prepared. Now, another interesting method obviously is this metal vapor co-condensation method, which is described right now. So, this is quite a common method for synthesizing various kinds of unusual organometallic compound, which otherwise by conventional method becomes not so easy to prepare. So, these are metal atom, ligand vapor, co-condensation method, and this is illustrated by this beautiful example in which molybdenum gas is reacted with C7H8 gas by this co-condensation method at minus 196 degree centigrade, and then slowly warming up to minus 30 degree centigrade gives this eta 6 bound molybdenum complex, which at 50 degree centigrade decomposes to this eta 7 eta 5 bind complex. So, the rate in which this converts is 3.4 10 to the power minus 3 per minute Kelvin, and heat molybdenum So, this is eta 7, eta 5, and this was eta 6, eta 6. So, what we see that this very unstable eta 6 combination is formed, which upon heating gets converted to this eta 7 eta 5 forms. So, this is a very interesting method in which one can see the rearrangement of the hapticity occurring from eta 6 to eta 7 eta 5. Now, with this we come to this end of discussion on various synthetic methods that are available for preparing these C6H7 based transition metal complexes, and we are going to be discussing the structure of these complexes. For example, for this particular compound, which is C5H5 vanadium C7H7, the structure is as shown over here. So, this distance between Cp to vanadium is 192 picometer, whereas vanadium to C7H7 is much shorter, and it is at 146 picometer, and the vanadium to one of the peripheral ring, this is about 226 picometer, and vanadium to one of the peripheral ring, this is about 219 picometer, and this carbon carbon bond is about 140 picometer. So, here we have a vanadium complex of the type which is shown. There is also eta 6 bound cycloheptatriene compound as is shown over here, and the X-ray does confirm that one of the ring is not a part of the planar ring, and one can sort of see that this is bound in a eta 6 fashion to molybdenum carbonyl, and this is C7H8 MoCO3. So, this the distance is about 134 picometer, and the other one is 146 picometer. So, it is between 134 146, whereas the hydrogens which are not part of the ring, that is even higher, 154 picometer. Now, this is eta 6 system. Similarly, one can look at C7H7 VCO3, which is something like eta 7 bound carbonyl. So, this distance is 230 picometer, and this is eta 7 bound. So, what we see over here that in this one also is eta 7 bound ring. So, what we see over here that in the eta 6 bound, one of the CH2 is indeed out of plane containing the other 6 carbons, and is projected out as is expected. So, with this I would like to conclude today's lecture, and in this lecture we have looked at various synthetic preparative methods available for preparing these transition metal C7H7 complexes. To begin with, we saw that these can be prepared by substitution reactions, and this substitution can reaction can proceed from the transition metal carbonyl complexes, then carbonyl moieties getting substituted by C7H7 or C7H8 ligands. We had also seen examples where mixed Cp metal chromium benzene complexes being reacted with C7H8, and as a result the benzene ligand giving way to C7H8 incoming ligand. We have also seen the other method apart from substitution are the reductive coupling method, in which a metal halide, a reducing agent, and C7H8 ligand is taken, and sometimes these eta 6 cyclohexatriene complexes are formed, which can be converted to eta 7 bound C7H7 complexes by simple abstraction with trittyl cation. We are also seen photochemical as well as chemical induction of sigma pi rearrangement, in which C7H7 ligand first bind in a eta 1 fashion, and then gradually with decarbonylation ends up becoming eta 3, and then finally to eta 5 fashion. And lastly, we see that this can also be produced by metal ligand co-condensation method. We have also looked at the structure, and we had seen that indeed for eta 7 is a planar structure, and whereas in eta 6 that these one of the CH2 system is completely out of the ring containing the 6 carbon atoms in C7H7 moiety. So, with this I would like to conclude today's lecture, and we are going to be talking more on the reactivity aspect of C7H7 transition metal complexes in the subsequent lecture. I sincerely thank you for bearing with for listening to me in this lecture, where we have taken up these preparative methods and structure of C7H7 transition metal complexes in quite detail, and we are going to be proceeding further by talking about its reactivity in the next class. So, till then, goodbye and thank you.